Okay, let's start the second part of this lecture. So, in the previous part, we talked about recombination. In this part, we're going to talk about generation, and specifically optical generation. The reason why we wanted to cover recombination in the previous part is that is going to balance out with optical generation of carriers to help us determine a net amount of carrier increase you get when you have optical generation. Because obviously, if you shine light on a semiconductor, the carrier concentration doesn't go to infinity, right? And so we need to understand recombination and how that counteracts optical generation. So, on that topic, besides temperature and doping, are there other ways to increase carriers? And of course we know one way to do that is just electrically inject them, right? That's what we do with p-n junctions. The other way you could do it is to bring in photons of light with energy greater than the band gap. Okay? If the energy of the photon coming in is not greater than the band gap energy, then you don't have enough energy to take an electron away from the valence of the semiconductor atom and take it up into the conduction band. So this photon, for example, has more energy than the band gap, takes an electron way up here. As you remove the electron, you create a hole. So for one photon, you get both a hole and an electron. And if the photon has much greater energy than just the band gap, as you can see here, the electron can go higher up in the conduction band and then go down and give up energy, because this is an energy band diagram, and give up that energy as heat, which is just phonons, which are vibrations of the atoms in the semiconductor lattice. So, before we look at optical generation, we also need to understand photons and how much energy they have. And so, let's first focus on a photon itself. This is what a photon looks like if you were to freeze it in time and look at the electric field and the magnetic field as they oscillate sinusoidally with time and distance. And so you'll notice here you've got electric field oscillating sinusoidally this way, and you've got magnetic field oscillating sinusoidally this way. Now, when we talk about photon generation in terms of how you generate light from a semiconductor, I'll explain a little bit more why of how you get an electric field which generates a magnetic field, which then generates electric field. So this is basically an electromagnetic disturbance based on Maxwell's equations, where a time-varying electric field results in a time-varying magnetic field and vice versa. And so all we do is we feed this energy and you start to get this electromagnetic disturbance which propagates forward. Now, it's important to remember for a photon that if you look at the wave equations for it, this tracks the E field here, and if you look inside the sinusoid, you've got two terms. You've got kx, meaning essentially freeze this in time. So don't change time, but vary distance x. That's what we see here, right? And so if I freeze this in time and just look versus distance x, traveling distance x in this direction, you can see you get sinusoidal behavior. And k is the wave number, which is 2 pi over lambda right here, okay? Lambda being the wavelength of the light. Now, the other part of this is the time-varying component, saying, okay, instead of freezing time, let's freeze position. So for example, let's look at the photon only in this plane right here at some position x that's constant. Well, if I were to basically allow this photon to propagate forward, as it moves forward through this plane, the same sinusoidal oscillation you see as it goes through the plane, I'll see the E field increase, decrease, decrease, and its back and forth motion will be sinusoidal. So basically the wave equation gives you both the appearance of the photon if you froze it in time and looked at it versus position, or if you freeze it in position and you look at it versus time. And then this is omega out front, which is 2 pi f, where f is the frequency. And you can calculate the frequency of the photon from the speed of light divided by the wavelength of the photon. Now, the key thing we need to remember for this lecture is that the energy of the photon can be calculated as hc over lambda, Planck's constant speed of light divided by wavelength. And the simple version you should remember for semiconductor systems is that it also can be given as 1240 divided by lambda in nanometers, okay? And so this is, most semiconductors emit or absorb light in the hundreds to thousands of nanometers range, and so this is a very convenient way to calculate it, where you don't have to basically put HC in there and calculate each time. You just 1240 over lambda in units of nanometers. You can see how that works out up here. Here I've plotted the visible spectrum here. As I decrease in wavelength, my energy should increase. Smaller lambda, this whole term should go up. Energy in electron volts should go up, and you can see that. Decreasing wavelengths, increasing energies of the photons in electron volts. Simple, quick calculation. Let's look at 620 nanometers right about here. If I put 620 in here, 1240 by 620 would be 2.0 electron volts. Okay. Way out here is the ultraviolet, very high energy photons, and here is the infrared, lower energy photons, both of those not being visible. Please remember that the visible spectrum is just a tiny, tiny part of a larger electromagnetic spectrum, which goes all the way from radio waves with very long wavelengths, and this is in meters, to gammas and X-rays with very short wavelengths over here and very high energies. So here's a question and a bit of a learning point. So why are gamma, X-ray, and UV harmful for us, they say? So all this stuff, why is this stuff harmful for the human body if you have too much exposure? But it's okay to basically every day for multiple hours in some cases, take a cell phone in the microwave regime, put it right next to your head and allow that microwave radiation to penetrate your brain. Well, the answer is simple. If you look at the energies in the visible spectrum, we're around 2 or so electron volts, right? So 2 to 3 electron volts. If you go to microwave, you can see that we are multiple orders of magnitude longer in wavelengths and lower in energy. So you're looking at thousands or tens of thousands or hundreds of thousands of an electron volt of energy. Tiny little bit of its energy for the photons. So those photons don't have enough energy to be harmful. So why does that make things like ultraviolet, gamma, and X-rays harmful? Well, when you go to ultraviolet light, the energies out here will start to get in the range of 4 to 5 electron volts. And it just so happens that if you look inside your body and at your DNA, the bonding strength for the molecules of your DNA is typically in the range of 3 to 5 electron volts, 3 to 6 or so electron volts. And so as soon as you get into ultraviolet photons or shorter, they have enough energy that they could go into your body, be absorbed by your DNA, have enough energy to break the DNA bond, and then rearrange it for you in a way it was unintended, one of the rearrangements being cancer. And so that's why shorter wavelength photons are generally dangerous for us if we have too much of a quantity of them, because you're just basically playing a probability game that one of those photons could rearrange your DNA in a harmful way. So, if it weren't for this optical generation caused by photons being absorbed in silicon, silicon would look like glass. But we know silicon doesn't look like glass. So, that's because of the fact that it absorbs visible light, so it looks dark. So what wavelengths of light will silicon absorb? Well, if I know the band gap energy of silicon is 1.12 eV, so the band gap energy is 1.12 eV, I can put that out front in this equation. I can back solve for lambda, and I will find that lambda less than or equal to 1.1 micron will be absorbed. Again, shorter wavelengths, higher energy. Anything less than 1.1 micron will have enough energy to generate an electron-hole pair. Take a guess for sapphire. What do you think its band gap is? Well, you can see it's clear, so you know its band gap is way out in the ultraviolet because all the visible light can get through sapphire. You can see that. Here's a question. For silicon, if I have a photon with less than 0.55 nanometers, or 0.55 microns, which is 550 nanometers or less, which means energy greater than 2.2 electron volts, if that's absorbed by silicon, which is true, would I get 1 or 2 electron hole pairs for each photon? Because this energy of the photon, for silicon, it would go way up here. The electron would go way up here, twice the band gap energy. So if I have twice the energy needed to generate an electron hole pair, could I get 2 electron hole pairs instead of 1? Well, the answer is no. As you can see in this diagram here, if you kick an electron even higher up because of a higher energy photon, it doesn't give you 2 electron hole pairs typically. Most of the time, probability favors it just coming down to the conduction band and giving up its energy as heat to the silicon. And so what's this tell you about silicon solar cells? Well, that tells you already that silicon solar cells, when they have sunlight on them, which has a lot of visible light, are not able to efficiently capture the energy of visible sunlight because for green or shorter, at least half of it is just going into generating heat in the solar cell and not into generating electron hole pairs, which are the electric carriers we want to collect to get energy out of the solar cell. So we'll cover that more in a couple lectures. Let's do another example. Let's say we hit silicon with 10 to the 10th photons of green light, which is 2.2 electron volts, every 1 microsecond, which is 10 to the 10th photons per 1 microsecond. 10 to the 10th divided by 10 to the minus 6 is 10 to the 16th per second. How much power is that? Do you think it's a lot or a little? Well, we'll do a simple calculation. 1 joule is 1 volt times 1 coulomb, right? An EV is a measure of energy in terms of joules, but it's not 1 joule, okay? If I look at 1 electron volt, it's one electron has a charge of 1.6 10 to the minus 19 coulombs, very small charge for 1 electron, and the equivalent volt for that would be the 2.2. And so you can see your total energy for 1 photon in joules is very small. If I want to calculate power, then I need joules per second. So this is the energy for each of those photons we had, 2.2 electron volts. I multiply that times the number of photons coming in per unit time, and you'll find out you get joules per second as a result, and I get 3.5 milliwatts. So you might think this is a ton of photons, but this is the equivalent of like a low power or low output LED in terms of the optical power coming out, or in terms of the optical power being absorbed. Okay? So again, remember that this is green light and it's hitting silicon, so half of the energy becomes electron hole pairs, half of it becomes heat because you kick them up here with excess energy and it comes down and gives off heat. And the electron hole pairs, if you do nothing, they'll just recombine at some point again, and that will become just heat also. And so the key point I'm making here is that if you shine light on just a silicon wafer, it's just going to get hot. It's not a useful device. We'll talk about how to make it into a useful device next time. But for now, one thing you could do is take a simple slab of silicon. Don't use it as a solar cell yet. We haven't told you how to do that. But how could I use it as a simple photodetector based on I equals V over R? Well, it's simple. If I shine light on this and I generate electron hole pairs, that should increase the conductivity, right? And so I could either measure the current through the silicon wafer with an applied voltage, or just directly measure the resistance and see that the resistance goes down as I shine light on the sample. So there is usefulness of this to make a very simple photodetector, but it's not ultra sensitive. Okay, so how many excess carriers do we generate? So if we already said that we can make a photodetector out of this because we shine light and we get excess carriers, well, how many excess carriers do you get? Well, if you want to calculate the optical generated excess carrier concentration, then you want to use this formula here. And this is for low-level injection conditions. Anytime you have a PN junction or optical illumination or anything where you're creating more carriers by injecting them somehow, then low-level injection means that the amount you're creating is always less than the doped or thermally generated amount. Why do we track that? Well, if I want to predict all the things like increased conductivity for a semiconductor wafer as light hits it, then all the parameters like mobility and things like that are based on a given doping level. That calculation gets more complicated if I am changing the background, if I'm changing the total concentration of electrons and holes above the dope level. And so if I'm not changing it above that, I can make simpler calculations. For example, if I have higher concentration, lifetime goes down as well, right? And so this formula assumes that you're generating carriers in excess, but it's not greater than the background doped or thermally generated amount, so terms like lifetime have not changed. So if I want to calculate the excess, here's the excess of electrons, which equals the excess of holes. That makes sense. Every time I generate an electron, I get a hole too. It's the optical generation rate times the lifetime. That should make sense because if I want carrier concentration out in front, which is per unit cc, and I have lifetime, which is going to give me units of seconds, then my optical generation rate is 1 over cc per second. Basically, how much concentration per unit time are you generated? And again, as we said before, the electron and hole lifetimes are equal, and so these are equivalent as well. Do a quick calculation. Let's hit silicon, 1 cc, to make it simple, with 10 to 13 photons of light every 1 microsecond. We'll assume the photons have enough energy to exceed the band gap and be absorbed. And we'll assume the minority carrier lifetimes are both 5 microseconds for the electrons and holes. Well, just the carrier lifetime. Doesn't matter which one's minority or majority. So my optical generation rate was 10 to the 13th per cc per microsecond. Okay. Remember I said this is every 1 microsecond, so we have to put that in there. So that'll be divided by 10 to the minus 6, which makes this total number bigger. And then I'll put that in here. I'll put my lifetime in here, which is also in microseconds. Okay? The microseconds will cancel out, and I end up with essentially 5 times 10 to the 13th. I get 5 times 10 to the 13th per cc extra carriers created, both electrons and holes, in this example of photons irradiated on 1 cubic centimeter of silicon. So what you can see here is that I need to pay attention to the generation, right? That's important. But I also have to pay attention to recombination because they're clearly balancing out. Generation's increasing, recombination, which is essentially lifetime, is decreasing. That's why we reviewed recombination on the previous slide. So what's the optical absorption look like? So if I have a slab of silicon here, do all the photons get absorbed like right here at the interface? Do most of them make it through? What happens? So how we can solve this is we'll set up a simple system here where we have, here's our photons coming in, and we'll say I'm starting with an intensity IZ right here at the interface. So here's the intensity I at a position Z to start. And then I'll say I have a new intensity at a distance DZ to the other side. So we'll say this silicon is DZ thick. So it's then the distance is Z plus DZ. Okay? Well, if this is the number of the intensity of the photons coming in, and this is the intensity coming out, then the difference between here and here would be how much is absorbed, right? So that's what I'm saying here with this equation. The amount you start with minus the amount that gets to the other side is the amount that is absorbed, and we could calculate that by the amount you start with, this coefficient alpha here, which is the amount absorbed over a distance dz times dz, which then gives you just the amount absorbed. I'll notice that this is a simple differential equation where this is diz. I'll move dz to the other side here. It's absorbing, it's decreasing in intensity, so I have a negative symbol here, a negative sign, because I'm losing the change of intensity versus distance is a decrease, right? The slope is negative, so I know I have a negative out here. And this is a simple first order linear differential equation. You could go to a book and solve it this way, or you could recognize that, well, this is pretty easy. The derivative of a function with respect to z is the same as that function times some constant. Well, that's easy. That's just an exponential, right? The derivative of an exponential, just some constant falls out. And so if you solve this differential equation, you'll find that your intensity as a function of distance is your intensity at position 0, starting right here. And it exponentially decreases with distance z through this thing. And so in this exponential, I've got two things. I've got distance z into the silicon, and I've got alpha, which is my absorption coefficient, which is in units of inverse centimeters. Again, that makes sense because centimeters times inverse centimeters, units cancel out. I can't have units up inside an exponential. So you can see this plotted here. This is intensity versus distance in the silicon, and it will decrease exponentially with distance, the intensity, and that shows you the absorption profile. If you have a small absorption coefficient, that means most of the light will get through. Here's a small absorption coefficient, not much decrease in the intensity as you go through the silicon. If you have a large absorption coefficient, this exponential gets stronger and you could have all the light be absorbed practically and none make it through the other side. Now, the absorption coefficient is different for different material systems and it changes with wavelength. So here's a plot of log of absorption coefficient. So if this is 2, that means the absorption coefficient is 100 here. This is a log of absorption coefficient versus wavelength in micrometers. You've got a bunch of different material systems here with different band gap energies. And just look at indium phosphide for an example here. Or let's look at silicon. Let's look at silicon here. So I'm decreasing wavelength and I get no absorption for silicon. You can see the absorption coefficient goes to 0 here for silicon. Eventually I get to wavelengths less than 1.1 micron, which, yep, that's what we said was the band gap energy for silicon in terms of wavelength. Where then all of a sudden, for shorter wavelengths than that, the absorption coefficient goes up because the silicon is able to absorb it. The photons have enough energy to generate electron-hole pairs. In fact, if you look at these curves, these will give you the band gap energies of these different semiconductors where you can see where the absorption profile starts to take off. Now, how thick does, let's do a sample calculation. How thick does a silicon wafer need to be to absorb 90% of 1 micron light? So if I'm at 1 micron here, I'll say, okay, 1 micron, I'll assume that I'm over here 2. Let's say that's log of 100. Okay, my absorption coefficient is 100 inverse centimeters. Okay, it's a little bit less on this plot, but let's say that's close enough. I will then calculate this using this equation. I'll put I naught back over here. If I'm absorbing 90%, only 10% gets through to the other side. I put in my minus 100 over here, minus alpha, alpha is 100, times z. I'll take the natural log of both sides, I'll solve for z, and I find that the silicon wafer has to be 230 micrometers thick to absorb 90% of 1 micron light. Let's do the same calculation for green light. Okay, well, green light is way out here, 550 nanometers. And the absorption coefficient for silicon is increased substantially. So if I do that calculation, I'll find that to absorb 90% of green light, the silicon wafer only has to be 2 micrometers thick. So you don't even need a wafer, it just has to be a thin film. And you can see that makes sense given the increase in absorption coefficient as you go to shorter wavelengths here. Okay, at this point you can take a break, but do this quick review before you do take a break. If I viewed a silicon wafer with night vision goggles where the light has less than 1.0 eV energy, would it look dark like it normally does, or will it be transparent like glass? You should be able to answer this. If the light is absorbed in a semiconductor, what's the mathematical profile that the intensity follows in terms of how it decreases? That's very simple, we just covered that. If I keep shining light on a semiconductor, the photons have energy greater than the band gap, what will the carrier populations do over time? There's only one right answer here. You should be able to get it pretty easily.